Hello, welcome back again. Today in this lecture I will talk about basic concepts and algorithms of association analysis, especially focus on algorithms and complexity and some optimizations that we could do to speed up or improve things. So when we look at the factors affecting complexity of Apriori, we need to deal with minimum support threshold. We also need to look at dimensionality. We need to look at the size of the database, especially the number of transactions in the database, and the average transaction width. So all these things affect the complexity of Apriori algorithm. We can change the minimum support threshold and include maybe more frequent item sets or decrease more frequent item sets, and that will directly affect the rules that are generated. Again, dimensionality, that is the number of items of the data set. It's about number of attributes in a sense. So the more we have, the more space we will need and count each of the items as during the process. So that will also increase I/O as well as computational speed, computational requirements. We talked about size of database, which relates to transaction size, as we have to do multiple passes while running the algorithm. That will definitely change things. Again, some transactions are including only few items while others are including many items. So on average, how many items are included in a transaction can also change the complexity of the algorithm. So if we look at this complexity, definitely size of item set is not helping, right? We know that. So if you look at on the top figure, we have size of item sets versus number of candidate item sets. So if we actually have about 10 items, so that's the size of item set, then based on support, let's say if we set it to 0.1, 0.2 or 0.5. So as you see, as we increase the support, the number of candidate item sets dramatically decreases, because when we have lower item sets, when we have a lower for support, likely we will include all possible combinations, and we increase that support and it will eliminate quite a bit of that because it will be pruned. Same thing here, different support here, and this is number of candidate item sets and this is number of frequent item sets. That will also change because frequency is counted, right? So we don't call every item set that's frequent, we call some item sets are frequent. So as we increase the support, then that will also increase, like with lower support, for instance, we have quite a bit frequent item sets in comparison to with a higher support. We eliminate or prune many of these and we will have fewer frequent item sets. Here, this is effect of support threshold on the number of candidate and frequent item sets. So if you look at the effect of average transaction width on the number of candidate and frequent item sets, again, as the so we know that if the width is 5, on average we have 5 items, for instance, versus on average we have 15 items. That will also, like when we have many more items, definitely that dramatically, these are on 10 to the 6, increases the number of things that we have to do in the algorithm, or comparisons, for instance. So here width is 15 versus width is 10 and width is 5. Width is 5. With 5 we don't even see it because this is 10 to the 6 scale. All these are 10 to 6. this must be 10 to the 6 or 5. This might be 10 to 5, but as you see, this actually increases huge by a change in width. Same graph here with width negatively affects it. So what can we do is, if we can somehow find a compact representation of frequent item sets that are redundant, then we can actually have improved the performance. So some item sets in this set here are redundant because they have identical support as their supersets. So you can look at it, we have almost replicated transactions, but if you look at these, are similar to each other. So maybe we can eliminate and use only things that we can live with. So if you look at how many number of frequent item sets do we have, because we have maximum transaction width is 10, so we have 3 times of that. So we need some other compact representation so we can actually eliminate number of comparisons during the processing. So for that we have maximal frequent item sets, and we will also talk about closed frequent item sets. An item set is maximal frequent if it is frequent and none of its immediate supersets is frequent. So it's sort of the border. Here AD, ACE, BCDE is frequent, but if you look at the children, we have only one children in this case, but we have multiple children for ACE. None of its children have more support than the parent. So in that case, this is frequent, but the children are infrequent. Here, if you take this one, AD, and you have 4 of these, all are infrequent. So this is sort of the place where it passes from frequent to infrequent. That's the location, but I cannot include AC here because AC is okay here, but it is still not covered by ACE. So this eliminates, but I have maximal item sets that are marked here. So if we can illustrate with an example, we can do a support threshold, let's say 5. This is 5 that we set. So these are items. For instance, A itself is not supported, as you can see that there is only 1. So C has only 3. So here we have F, that is 5, and we do have J as well as, no, the AJ is 4, sorry, only F is 5. So F is supported. So this is the maximum frequent item set if it's the threshold is set to 5. It's the only one actually. If we set support count threshold count by 4, then I have many more, right? So F is definitely going to be there, E is going to be there, EF is going to be there, and J is going to be there. So EF, EF, J. And if you do 3, I can actually quickly look at it. So we have 3 all subsets of C, D, E, F, because this has 3, right? So I can actually only consider this one and its subsets because these are already covered, plus this one, and yeah, that's only this one, plus that one, J. So what are maximal item sets? Now that's the question. What are the maximal item sets? For support threshold, there's only 5, right? So we have only 1, F. So what about this other one? Support threshold by count 4. So this is maximum. So we are trying to find maximal item sets. So just give you a minute and you will definitely see that it is EF together this time and J. So J is still itself is going to satisfy that. So none of its children is going to be more than that, right? And here EF. So if you take EF together, you can actually, you are trying to get the maximum out of it, right? So EF together has 4, and combinations underneath is by itself F has more than that, but together that's the only one. So this is where you have 4 support, and above that you can have actually F, but that's exceeding that. So this is where I have the maximum EF together. Here if I set maximal threshold, 3 support threshold to 3, again this time I have CDEF plus J. So let's look at the definition again. So we have association similar to that, and so we have things that are less, but here we are at the borderline, and this becomes, these are frequent subsets, but superset is infrequent. So let's look at this one again. You can quickly look at it. Support threshold by count, maximal item sets A, B, C, D. If it is 5, because I have A, that is 5, 1, 2, 3, 4, 5. There is B itself is 5, and C itself is 5. But pay attention, they are not overlapping. When I set the 4, definitely I can take AB, right? That is 4. Then I have AC, because there is this overlap here. Then I have BC, not including these, but 4 is still satisfied. And if you set it to 3, then you have only this one, and everything else is actually covered underneath that. So this will actually help me reduce the size of the things that I can process. What is closed item set? An item set X is closed if none of its immediate supersets has the same support as the item set X. So you can look at item set here A. A has 4, and you look what is its supersets A, AB, which is 4 too. So this is not included. So I'm not including A here, right? Because its children has the same support. Likely I cannot exceed, you know that I won't be able to exceed, so I have to be less. Same is not accepted. But if you look at B, that's 5, and that's the maximum that I can automatically mark this. But the practice here is, if you take B, you look at AB, which is 4, BC, which is 3, BD, which is 4, ABD, that's 3, BCD, that's 2, ABCD, that's 2. So as you see, B is 5, and the immediate supersets of this, like AB, BC, BD, they are less. So that I know is closed. So I can mark that. That's a closed item set. So that's sort of how you can proceed. And how do you get the support count? You are actually looking at the transactions. This is how you can actually reword it. X is not closed if at least one of its immediate supersets has support count as X. So you can look at this set here. So in this set we will find the closed and maximal item sets. So just pause for a minute and think which one will have more. We will see more closed item sets or more maximal item sets. So this is something to think about for a moment before I give you an immediate answer to that. And so Okay, so I will continue. So these are transaction numbers 1, 2, 4. So there's 1, 2, 4. These are transaction numbers 1, 2, 3, 1, 3, 4. These are transaction IDs. These are, I would have probably put it with comma, but don't think this is 1, 2, 4 as a single digit number. It is, these are 1, 2, 4. So these are transaction IDs. So and if here A has 3 transactions, it's included in 3 transactions, so that's the support count, right, for A. Here 1, 2 and 4, so that is the support of A. So if I look at the children of A, I see AC, which has the same support count. So A cannot be closed, right? If you look at B, 1, that's 3, and there's that, which is also, oh sorry, this is not B related to B, but BC is also same support count. So you can go through this, and definitely C is here closed, right? And you can go through this and process. So, and at the end we have a transaction A, B, C, D, E, but none of the transactions support that. So it is actually no transaction marked on it. But as you can see, I should be dropping. As I go down from the 3, I should be dropping. And when I don't have, these are to actually identify closed item sets. So, and I will also show you in this. So if we set minimum support to 2, because this is important for maximal frequent item sets. So if I set the support to 2, I can show you these closed. You don't need the minimum support, you can just mark it. But for maximal you need the minimum support, because that's where you actually define where you are frequent and where you are also infrequent. So closed, these are closed. You can look at individual transactions, and that can be tedious to look at each of these, but let's say why this is, for instance, closed, because there's 2, 4, there's 2 transactions supporting, and children has 2 and 4, so there's only 1 transaction in each. So, and if you count how many transactions are closed without considering the support, then you will see there are 9 of them. A, C, D, E, A, C, B, C, C, E, D, E, A, B, C, A, C, D. So these are also closed. But what is maximal here is, maximal is always a subset of closed frequent item sets. So among these candidates, this is frequent, and I'm not marking this as maximal because it has a children here, ABC, which is also frequent. So I have to choose the border. So if 2 is support count, ABC is 2, but then ABCD is only 1. So this is infrequent. This is infrequent. It's not even supported. This is infrequent. AB. So ABC has this one, and only these 2. Yeah, that's only these 2. So if you look at it, only 1 transaction there is that supports, and that has only 1 candidate, and this is becoming infrequent in that, for that reason. So if you look at, for instance, CE, I have ACE, that's only 1 transaction, BCE, that's 1 transaction, and CD, that's only 1 transaction. So that means I have support of 2, which is satisfying the minimum requirement, but all the children has only 1 transaction that's supporting. So this becomes the maximal frequent item set. So among 9, we have 4 of them that are maximal frequent item sets. So computationally it's much easier to work with closed frequent item sets because you just look at children and eliminate. But if you try to identify maximal, then you need to also do a little bit more competition. But definitely that will also help you in terms of space because you have to use less of items. So here we have closed item sets. So we have CD. Okay, so what are closed? C is closed because it's children. You can look at it. If it was we were looking maximal frequent, we will take CD together. But here I'm looking at C itself as well as CD. So both of them are actually, so C doesn't have any children, but CD also together has closed item sets. So now you can quickly look at it. This example here, these are support counts that are obtained from this table. So there's definitely CDE that is supported by 2, and these are subsets. So these are the only 2 that are closed. C that has 3, and so the children of C, for instance, CD that is less than C, CE that's less than CD, that's less than 3, right? So that's why I actually choose C as a closed item set, and also can also take CDs together because I have CD as a whole. I have 2 and I don't have any more, and that's closed item set. So if I was looking maximal frequent item set, then I will take CD as single entity. So you have a case here. Again, this is another example where we have closed item sets CDEF and also CF. Here's another item set. C and F are individually closed. So note that we have frequent item sets and we have closed frequent item sets and we have maximal frequent item sets. So frequent item sets is a lot larger in terms of space that's requiring. Closed frequent item set is a subset of that, and maximal frequent item set is even further subset of that, and this should be okay for this lecture. So we covered basically how we can computationally make less of a item set that we need to deal with for rule generation. See you in other lectures.